Professor Belfrost's computer science class is back!
Hi, welcome back. And today we will continue our last lesson on processor. And today we will cover much more concepts than before. So please prepare and let's review for our last lesson. Okay, so first point is very important that the processor consists of registers, the ALU, the instruction execution unit, a control unit, and interconnections among these components. The CU, okay, is that portion of the processor that actually causes things to happen. It issues control signals external to the processor to cause data exchange with memory and I/O modules. Also, it issues control signal internal to the processor to move data between registers to cause the ALU to perform a specified function and to regulate other internal operations. The execution of a program consists of the sequential execution of the instructions. Each instruction is executed during an instruction cycle made up of several subcycles. And execution of each subcycle involves one or more sort of operation which are called operations. Fetch cycle occurs at the beginning and causes instruction to be fetched from memory. There are four registers that involve MER, MBR, PC, and IR. For indirect cycle, once an instruction is fetched, then the next step is to fetch the source operands. And if the instruction specifies indirect address, then indirect cycle must precede the execute cycle. Third is that at the completion of the execute cycle, the test is made to determine whether any enabled interrupts have occurred. If so, then the interrupt cycle will be called. All will occurs. Then we know that the fetch, indirect, and interrupt cycles are really simple and it's predictable because each involves a small fixed sequence of micro operations, and in each case that the same micro operations are repeated each time around. But it's not true for the execute cycle because of the variety of opcodes. There are a number of different sequences of micro operations that may occur. So we'll see that all micro operations that we have discussed in the last lesson fall into one of the following categories: transfer data from one register to another, transfer data from one register to external interface, transfer data from external interface to a register, perform AL operation using registers for input and output. And control unit perform actually just two basic tasks. First is sequencing, that is causing the processor to step through a series of microoperations in a proper sequence based on a program being executed. The second is execution, which causing each microoperation to be performed. Okay, that. So we are focusing on our today's discussion. And yeah, we have defined so far the elements that make up the processor ALU registers that are fed and the micro operations that are performed. So for the control unit to perform its functions, it must have inputs that allow it to determine the state of the system and outputs that allow it to control the behavior of the system. And these are the external specifications of the control unit. And internally, the control unit must have the logic required to perform its sequencing and execution function. So here's the block diagram that you need to pay attention along this lesson in this today tutorial. Okay, please pay attention to this. If necessary, please take a screenshot. Okay. So from this block diagram given, we can see that there are some inputs, and the inputs are first is clock, which is how the control unit keeps time. Okay, so the control unit causes one microoperation or set of simultaneous microoperations to be performed for each clock pulse, and this is sometimes referred to as the processor cycle time or the clock cycle time. The second is instruction register. So the opcode and the addressing mode of the current instruction are used to determine which microoperations to perform during the execute cycle. Third is flags. Okay, so these are needed by the control unit to determine the status of the processor and the outcome of previous ALU operations. For example, for I set instruction and the CU will increment the PC if the zero flag is set. The fourth is control signals from the control bus. The control bus portion of the system bus provides signals to the control unit, and this very important. Okay, and fifth, control signals within the processor, and these are consist of two types. Okay, those that cause data to be moved from one register to another, and those that activate specific ALU functions. Sixth, it is control signals to control bus. Okay, these are also two types: control signals to memory and control signals to the I/O modules. Okay, so there are three types of control signal used: those that activate an ALU function, those that activate a data path, and those that are signals on the external system bus or other external interface. And all of these signals actually ultimately applied directly as binary inputs to individual logic gates. So let us consider again today the fetch cycle to see how the control unit maintains control. So the control unit keeps track of where it is in the instruction cycle. At a given point knows that the fetch cycle is to be performed next. Then the first step is to transfer the contents of the PC to the MAR. The control unit does this by activating a control signal that opens the gates between the bits of the PC and the bits of the MAR. The next step is to read a word from memory into the MBR and increment the PC. And the control unit does this by sending the following control signals simultaneously. Okay, so first is control signal that opens gate allowing the contents of the MR to flow onto the address bus. Then the memory control signal on the control bus. Control signal that opens the gate allowing the contents of the data bus to be stored in the MBR. Control signals to logic that add 1 to the contents of the PC and store the result back in the PC. By following this, the control unit sends a control signal that opens gate between the NBR and the IR. This is very important actually. And this completes the fetch cycle except for one thing. The control unit must decide whether to perform an indirect cycle or an execute cycle next. To decide this, then it examines the IR to see if an indirect memory reference is made. The indirect and interrupt cycles work similarly. For the execute cycle, the control unit begins by examining the opcode and on the basis of that, then decide which sequence of microoperation to perform for the execute cycle. Okay, so here is a very simple example for you related to the functioning of control signals shown with simple processor with a single accumulator or sort as AC. Okay, so you can see it. This diagram will be used for several times. This it's worth to take screenshot. Okay. So the data paths between elements are indicated on the previous figure, and the control paths for signal emanating from the control unit are not shown, but the termination of the control signal are labeled as CI and indicated by a circle. Okay. So the control unit receives input from the clock, the instruction registers, and the flags. With each clock cycle, the control unit reads all of its input and emits a set of control signals. Control signals go to three separate destinations. First is data paths. These will control the internal flow of the data. Okay, and for each path to be controlled, there is a switch. Okay, a control signal from the control unit temporarily opens the gate to let data pass. The second one is ALU. So it will control the operation of the ALU by a set of control signals. The signal activates various logic circuits and gates within the ALU. The third one is system bus. So it sends control signals out onto the control lines of the system bus. So the control unit must maintain knowledge of where it is in the instruction cycle. By using this knowledge and by reading all of its input, then the control signal emits a sequence of control signals that causes microoperation to occur. It uses clock pulses to time the sequence of events and allowing time between events for signal level to stabilize. Okay, so here's a table that we'll also use for several times in this lesson that indicates the control signals that are needed for some of the microoperation sequences described earlier. For simplicity, in the data and control paths for incrementing the PC and for loading the fixed addresses into the PC and MAR are not shown in this table. It's worth taking a screenshot. Okay. So it is worth pondering the minimal nature of the control. So the CPU is the engine that runs the entire computer, and it does this based on only knowing the instruction to be executed and the nature of the result of arithmetic and logical operations. And it never gets to see the data being processed or the actual results produced. It controls everything with a few control signals and points within the processor and a few control signals to the system bus. Okay, so that's done. Now let's discuss about internal processor organization. The example figure that we have discussed before indicating the use of a variety of data paths, and this complexity of this type of organization should be clear, and sometimes it will cause a headache. Using an internal processor bus, however, the previous figure can be rearranged as shown in following picture in the next slide actually. A single internal bus connects the ALU and all processor registers, and control signals are provided for movement of data onto and off the bus from each register. Additional counter signals control data transfer to and from the system, signal bus, and the operation of the ALU. Here's the picture. I rotate it 90 degrees, so maybe you need to rotate your head, okay, to see this. Okay, so there are two new registers present here, okay, labeled Y and Z, that have been added to this organization, and these are needed for the proper operation of the ALU. When an operation involving two operands is performed, the one can be obtained from internal bus, but the other must be obtained from another source. The AC could be used for this purpose, but this limits the flexibility of the system and would not work with a processor with multiple general purpose registers. Register Y provides temporary storage for the other input. The ALU is a combinatorial circuit with no internal storage. What is ALU and what is a combinatorial circuit? ALU will be discussed after CU, okay? Maybe in the next, maybe two videos again, okay? After maybe next week, the next 2 weeks, okay, ALU. But what is combinatorial circuit? Actually, we will cover these two, but maybe after we have covering all the basics of computer, we'll start discussing about what is combinatorial circuit, what is sequential circuit, whatever. Okay. Thus, when control signals activate an ALU system, ALU function, I mean, the input to the ALU is transferred to the output. Thus, the output of the ALU cannot be directly connected to the bus because its output will feed back to the input. Okay, now there's register Y. How about register Z? Register Z also actually provides temporary outputs, temporary storage, but this is for output. Okay. With this arrangement, then an operation to add a value from memory to the AC will have the following steps, as shown on this slide. Actually, other organizations are possible, but in general, some sort of internal bus or set of internal buses is used. The use of common data paths simplifies the interconnection layout and the control of the processor. Another practical reason for the use of internal bus is to save space. Okay, so we have discussed the control unit in terms of its input, output, and functions. And now turn to the topic of control unit implementation. Actually, there are a wide variety of techniques that have been used, but most of these actually fall into one of these two categories. The first one is hardware implementation. The second one is microprogram implementation. Because actually, both of these actually have a dedicated um, uh, explanation for it. I will focus on hardwire implementation for this video, and the next video will focus on microprogram implementation. Okay. So let's start from hardwire implementation. So in a hardware implementation, the control unit is essentially a state machine circuit. What is state machine circuit? It also will be discussed uh, with combinatorial and sequential circuit. Maybe this after we have done with the basic concepts of computer. Okay. These input logic signals are transformed into a set of output logic signals, which are the control signals. Okay. The control unit we have discussed having key inputs of the instruction register, the clock, flags, and control bus signals. In the case of the flags and control bus signals, each individual bit actually typically have sound meaning. The other two inputs, however, are not directly useful to the control unit. First, I consider the instruction register. The control unit makes use of opcode and will perform the different actions or different instructions. To simplify the control unit logic, there should be a unique logic input for each opcode, and this function can be performed by a decoder, which takes an encoded input and produces a single output. In general, a decoder actually will have n binary inputs and 2 raised to the n binary outputs. So the 2 to the n during input parents will activate a single unique output. Here's the table that shows an example for the decoder with n equals 4. Okay, so yeah, actually you don't really need to understand this for this time. Okay, let's move on. So the clock portion of the control unit issues a repetitive sequence of pulses, and this is useful for measuring the duration of microoperations. Essentially, the period of the clock pulses must be long enough to allow the propagation of signals along data paths and through processor circuitry. However, as we have seen, the control unit emits different kind of signals at different time units within a single instruction cycle. Thus, we would like a counter as input to the control unit with a different counter signal being used for T1, T2, and so forth. At the end of an instruction cycle, then the control unit must feed back to the counter to reinitialize it at T1. With these two refinements, then the CU can be depicted as shown. So to define the outward implementation of a control unit, all that remains is to discuss the internal logic of the control unit that produces output control signals as a function of its input signals. So essentially, what must be done for each control signal is to derive a Boolean expression of that signal as a function of the inputs. And this is best explained by an example. So let's consider again a simple example that has been illustrated before with its table too. So here's the unit. Okay, maybe if you have the picture, you have captured the figure below before, then it should it's not necessary for you to retake it again. Okay. So we saw in the table that the microoperation sequences and control signals needed to control three of the four phases of the instruction cycle. Okay, so let us consider a single control signal, say C5. Okay, this signal causes data to be read from the external data bus into the MBR, and we can see that it is used twice in this table. Okay, let us define two new control signals, P and Q, that have the following interpretation: fetch, indirect, for execute, and interrupt. Then the Boolean expression defines C5 is C5 equals P naught Q naught T2 plus P naught Q T2. What is this? This is Boolean expression actually, but we will discuss it later. Okay, what is Boolean expression? This is just simple logic actually. Okay, and that is the control signal C5 will be asserted during the second time you have both the fetch and indirect cycle. T2 because it only left with T2. Okay, this expression is not complete though, because C5 is also needed during the execute cycle. For a simple example, let us assume that there are only three instructions that are read from memory: LDA, add, and end. And now you can define C5 as P naught Q naught T2 plus P naught Q T2 plus P Q naught times LDA plus add plus n times T2. And this same process could be repeated for every counter signal generated by the processor. The result will be a set of Boolean equations that define the behavior of the control unit and hence of the processor. Okay, so to tie everything together, the control unit must control the state of the instruction cycle. And as was mentioned before, at the end of each subcycle, the control unit will issue a signal that causes the time generator to reinitialize and issues T1. And the control unit must also set the appropriate value of P and Q to define the next subcycle to be performed. We should be able to appreciate that in a modern complex processor, the number of Boolean equations needed to define the control is very large, and the task of implementing a combinatorial circuit that satisfies all of these equations becomes extremely difficult. And this results in a far much simpler approach, which is called as microprogramming, and this is mostly used now. Okay. So, okay, let's discuss a little about microprogramming. This is the introduction of microprogramming today. Okay, I will have one or two more videos to discuss about microprogramming in depth. Okay, so the term microprogramming or microprogram actually first coined by M.V. Wilkes. Okay, Sir M.V. Wilkes in the early 1950s. Okay, so Wilkes proposed an approach to control unit design that was organized and systematic and avoided the complexities of a hardware implementation. The idea intrigued many researchers but appeared unworkable because it will require a fast, relative, expensive control memory. state of the microprogram was reviewed by Datamation in its February 1964 issue. And actually, there are no microprogramming system was in wide use at that time, and the then popular view that the future of microprogramming is somewhat cloudy. None of the major manufacturers has evidence interest in the technique, although presumably all have examined it. But this situation changed dramatically within a very few months when IBM System SAS 360 was announced in April, and all but the largest models were microprogrammed. Although the 360 series predated the availability of semiconductor ROM, the advantages of microprogramming were compelling enough for IBM to make this move. And microprogramming became a popular technique for implementing the control unit of CISC process. So later we'll have what called CISC and RISC, and we'll also have a in-depth discussion about this. Okay, this is just the architecture of the processor actually. Okay, for the how much instruction sets actually needed for the processor. Okay. Okay, so in recent years, microprogramming has become less used, but remains a tool available to computer designers. For example, as we have seen on the Pentium 4, then the machine instructions are converted into RISC-like format, most of which are executed without the use of microprogramming. However, some of the instructions are actually executed using microprogramming. Okay, so to understand about microprogramming, then we need to start from understanding about micro instruction. What is micro instruction? So actually, the control unit seems a reasonably simple device, and nevertheless, to implement a control unit as a connection of basic logical elements is actually not an easy task. And this design actually include logic for sequencing through microoperations, for executing microoperations, for interpreting opcodes, and for making decisions based on the ALU flags. It is difficult actually to design and test such as a piece of hardware. And furthermore, the design is relatively inflexible. For example, say that it's difficult to change the design if one wishes to add a new machine instruction. So an alternative which has been used in many CISC processors is to implement a microprogram control unit. Okay, so please consider this table, which shows the machine instruction sets for well-cast example. As you can see, it is the use of control signal. Each microoperation is described in symbolic notation in this table. And this notation actually looks suspicious like a programming language. Yeah, actually, in fact, it is a language which is known as microprogramming language. And each line of previous table describes a set of microoperations occurring at one time and is known as microinstruction. A sequence of instructions is known as microprogram or a firmware. And this latter term reflects the fact that a microprogram is midway between hardware and software. It is easier to design in firmware than hardware, but it's more difficult to write a firmware program than a software program. So how can we use the concept of microprogramming to implement a control unit? Consider that for its microoperation, all that the control unit is allowed to do is to generate a set of control signals. Okay. Thus, for any microoperation, its control line emanating from the control unit is either on or off. This condition can of course be represented by a binary digit for its control line. So we could construct a control word in which each bit represents one control line. And then each microoperation would be represented by a different pattern of ones and zeros in the control word. Okay, that's enough for today. We'll continue our discussion on microinstructions and microprogramming in later video. Okay, so here's the quote for you today. So Bertolt Brecht once said, "Because things are the way they are, things will not stay the way they are." Do you understand this mean? Okay, it means that actually everything will change. I need to prepare for that change. Always keep moving and keep adapting, adjusting for any moment of change, and you will learn something that's precious in your life. Okay, so thanks for watching. This was to list. First, subscribe. Second, like, comment, and share this video to your friend. I'll be back every Monday, so keep watching. Be thoughtful. Goodbye. See you all.